they okay, great. So the microwave clocks, you were saying that they were fast turn on seconds instead of hours, and then they were competitive, superior in accuracy to the current common thermal.
Essentially they're comparable in performance to there's a small performance increase, but it's not an order of magnitude, which is what you'd like. When you start going to optical clocks, you start getting orders of magnitude performance improvement over current, essentially laboratory standard. So what we're doing with the microwave clocks is we're taking laboratory standard performance in terms of what's known as fractional instability, which is how much of a second you're off. And we're transmitting it to a platform that can be fielded. In terms of optical clocks, you're doing the same thing. You're generating a fieldable technology, but now you're having 10 to 100 times better performance. And the reason why it's a slightly bigger challenge to field optical clocks is you need frequency combs. Frequency combs currently are relatively large. There are a number of R&D efforts in micro combs, technologies that generate these optical frequency combs using very small structures, but there's still very much a lab development. So we have a partnership with a local laser company that's developing frequency combs for deployment. They're still a bit big, but will be intersecting the kind of the R&D environment in order to get these things down to a size that's maybe even half rack eventually. So we have one microwave clock program, Coldquanta microwave clock program. We have 3 optical clock programs, and they're all targeting slightly different performance and form factor characteristics, just in 3 very separate ways. And then there's a DARPA program that's starting up in both compact optical clocks and in larger lattice clocks for very, very long range development.
Okay. And then the optical clocks, you discussed transportable, which fits onto a Jeep or something like that. And then the smaller size was called what? The mobile or?
Yeah, so it's described in terms of the recent DARPA call. It's portable and transportable. Portable being 5 liters, which is roughly 2U, give or take. And then the other one is 200 liters, which is, a moderate refrigerator.
Right.
So that's kind of the distinction between the two.
Right. 200 liters, roughly the size of a oil gallon, or not oil gallon, but the 40 gallon.
50 gallon drum, 40 gallon drum.
Gallon drum, yeah. And so you mentioned that the optical ones would be good for 6G communications. Is there any 5G communications or like, kind of advanced 5G that would be using that kind of timing system?
We expect so. The G deployments are a spectrum, right? They're not. Right. It's not. It's all on and all off. So we expect to catch the tail end of 5G, but ahead of the 6G, the 6th generation communication system. So that's going to be the idea. That's going to be the sweet spot for our optical combs. The sweet spot for our optical clocks. The sweet spot for our microwave clocks is going to be likely going to be more targeted applications in commercial and in deployed applications in military.
So would they be, in theory, going to every cell tower? I think there's 5 million cell towers or something like that around the world, something like that? Would you need to have?
Ideally, yeah. It really depends on what the specification for 6G is going to end up being, which hasn't been established yet. But having a assured frequency reference in every cell tower doesn't require link up to GPS is likely going to be a factor in the next generation of commercial communications. We also have, I just want to make sure we note, a technology line in what we call quantum RF, And quantum RF is the concept that you can take atoms and you can use them as the receivers for a RF communication system. And they will replace both the antenna and the front end electronics on the communication system. We've had a program in quantum RF for 4 years now. Again, it spans both military applications and potentially commercial applications, but they're mostly driven by military defense R&D funding. So there's been a program at DARPA for the last year across 2 program offices in very, very compact systems for quantum RF. So quantum RF, it's kind of a brilliant, the physics of it is brilliant. Every atom is happily, sitting there with its electrons in their states. If you excite the outer electron to a highly excited state, it starts to look like an electrical dipole and a little antenna. If you take all of those antennas and squeeze them down into a condensed vapor, then they all start to respond identically to RF energy. If you control that state very, very carefully, then it's very selective to a very specific frequency of energy, and it's all still the size of an atom. It's not really any bigger. So they don't scale in size the way traditional antennas do with the wavelength. So in a traditional RF technology, the actual receiving element has some size scalability to the wavelength. So at very high, very low frequencies, at very long wavelengths, you need very, very large antennas. So, UHF, VHF, you start talking about the antennas in terms of feet, but these atoms can happily receive just in very small cell size. And they don't actually have to change their size in order to respond to larger parts of the spectrum. So the systems are both very, very small, and they also have extremely broad spectrum that they can scan between. They're small, they're selective. So the actual frequency, if you think of an old AM radio, the actual width of the resonator that's being selective to a specific frequency is very, very narrow. But they're simply able to scan over very, very large ranges by tuning the laser that's on them. So they're optically excited. It's the same technique we use in our quantum computer, known as a Rydberg atom. But they are, again, both small, have very wide range, and very selective, and they generally have sensitivity that's 10 to 20 dB better than conventional systems. At least that's what our current programs are targeting. So with higher sensitivity, you potentially have lower transmission requirements from the individual handsets for, say, consumer applications. At 20 dB, you're looking at 100 times better, say, battery lifetime, if you're able to achieve that kind of difficult but potentially valuable goal of 20 dB better than current receiver systems. And you're also able to do it in a sensor head, a receiver head that's much, much smaller than conventional systems. It can also be tethered. You don't actually have to have the low noise amplifiers directly on the system, although that would be fantastic. So you could run them on your receiver system and then tether them to the base station in a way that doesn't require as much infrastructure that current cell towers require. So, and then actually, I didn't mean to bury the lead. The most exciting part of these things is they work very, very well at high frequencies, the frequencies that are kind of most attractive for future communication systems, up in the gigahertz. They potentially are going to work all the way up to 300 gigahertz. So you have that 100 to 300 gigahertz area that nobody's really accessing right now because there's no technology available. You potentially have continuous coverage across that range. And so you're able to access part of the spectrum that no current technology can access. So across all these things, you have extremely valuable technology, both for comms as well as the intelligence community is very interested in these things. So we just responded to an IARPA solicitation. The intelligence community is very interested in the high sensitivity at very low size, as you can imagine. And the defense community is really interested in replacing disparate communications technologies with a single wideband, ultra wideband technology that can replace, you know, you look at a Navy ship and all the mass with the communication systems on, potentially replacing that with a single technology. So it's very, very exciting. One of our technologies is looking specifically at very, very high sensitivity at a select spectral band. And the way we're doing that is by integrating into our cell technology essentially antenna elements, pieces of metal that couple the RF energy directly to the atoms themselves in order to maximize the sensitivity at a very specific frequency. And then the other one is looking at the wideband capabilities. Essentially, it's looking at going all the way from the high kilohertz up into the low gigahertz in a single system. So it's a interesting approach, and it's kind of rapidly accelerating right now.
So RF technology, highly fundamental to, like say, communications. It also is the basis of the Internet of Things. All that at low power, other frequency ranges, Internet of Things is basically RF. So there is, they say, a mass multitude of applications for that. But to get for Internet of Things applications, you need to have smaller, low cost. You know, less than $1,000 per receiver. So, but if you can do that, you can scale it, then you're selling millions, perhaps even billions of devices.
Yeah, there's two parts to that question. So the technology I just described doesn't do transmit, right? It's not a transmitter technology, it's a receiver technology. So what it enables, the higher sensitivity enables you to use the kind of emerging 3.5 technologies in low power transmission at these higher frequencies, right? Because most of those technologies don't have sufficient transmit power to really enable anything. But if you start getting more sensitive receivers, then that is essentially enabling this lower cost integrated transmit technology. So that's one part of it. So we expect to work very closely with those vendors in order to kind of define the technology pairing that'll work at high frequencies and low powers. The second part is a little more critical. Yes, we are generally, at least right now, a technology that looks very expensive, and it's because the laser systems are very expensive. All of our laser systems require very narrow line width, scientific grade lasers, right? It's not something that's been commoditized or mass produced. Coldquanta is changing that. We are developing laser technology that's much cheaper, but targeted for the wavelengths and the technologies that are most exciting in quantum. And this quantum RF is a really good example of a technology that could take advantage of that. The specific tuning and coupling lasers required for this technology can be very, very well specified, and they can take advantage of the cost down available in diode lasers in order to enable low cost receive solutions. You're not going to likely, I don't want to say never, it's probably going to be a slightly different methodology than you'd expect from every cell phone having these things in them. They're more likely to be a centralized system that really takes advantage of the sensitivity and the bandwidth advantages. So for Internet of Things, you can think of a bunch of disparate little things all connecting to a central node and taking advantage of the ultra wide bandwidth and the multi-channel spectrum, which is essentially high capacity of a single centralized communications node. So you have a lot of very, very low power transmit technology, all communicating to a centralized node that has this ultra wide bandwidth, high bit rate capacity enabled by quantum. that's one vision of the future that would really take advantage of the capabilities of this technology.
So then you would have, instead of, say, 1,000 receivers in a massive warehouse, you could have one or maybe four receivers,
yeah.
one receiver in the warehouse.
That's exactly right.
And then and then you would have more precision, more accuracy, be able to like locate the device down to a centimeter instead of a meter or something like that.
Yeah, that's actually a different part of the problem, but something that is also enabled by quantum RF. So we have 3.5 active projects in this area. Mm-hmm. 2 of them are focused on the sensitivity and the bandwidth. The third one is the vector information. Mm-hmm. So there's a number of ways of getting vector information, identifying where the signal is coming from. One is to create an array. So one of our programs is looking at creating arrays of receiver heads using this technology. And that is both vector information, essentially direction, angle of arrival information. And then the second is you can do more advanced applications like phased array applications eventually. But the second way of doing that is to actually take advantage of the intrinsic phase and polarization capability of quantum in order to integrate that into a single head. And we have a long-running program for the Air Force that is looking specifically at angle of arrival using quantum systems. So all of that is enabled by quantum RF. And you could potentially integrate all of the capabilities into a single system. Directionality, high sensitivity, wide bandwidth, and high selectivity.
That's it. Incredibly exciting. So when do you think a ballpark estimate of a first of a kind commercial product might be possible with such a receiver?
So with the cost downs that are occurring with Coldquanta's kind of initiative in photonics, this particular technology we would expect to have prototypes that are sufficient for deployment, at least testing, in the 2024-2025 type of timescale. So our current, that's both when our current development programs hit their prototyping deadlines, as well as kind of intersecting with our current developments in photonics.
And you wouldn't have to have the same price targets, because if you're replacing $100,000 devices, your thing could cost $50K and you're still the price winner. And then you have the other features of it being better, more precise, etc. So then, your first commercial device could be $100,000 and you're still good because you're replacing hardware that's shorter range, blah, blah, blah. You need 1,000 of those other old things. So
that's actually one of the big advantages. So, right now the systems look expensive, but even if you're thinking about the current capabilities using relatively expensive off-the-shelf laser systems, they would still replace many, many, many different receiver technologies with the same system. And that has, again, kind of a capabilities improvement for military applications, but for consumer or commercial applications where you're just looking at cost, it's comparable to potentially replacing large comm space stations with a single quantum based system.
So Starlink, with their I think phased array or planar receiver now, I think they have a new second generation one that's flat. So would definitely it's not at some point your thing would be applicable to that, but then so other low Earth orbit kind of receiver things, if you make it smaller, then what had to be difficult to transport becomes something you stick in a car, stick in a truck. Applications open up if you have that mobility, and then the 300 gigahertz means that you're up to 100 gigabyte or gigabit communication rates by having the receiver being able to handle it, if the transmitter can handle that load.
That's right. Yeah. So for conventional, for high frequency comms type applications, for space-based stuff, when you're trying to replace conventional systems and you're allowed to have a very high value replacement system, I think that's a kind of an ideal first application. I do want to mention for space, there's some really interesting kind of crazy applications that are enabled by this technology. When you're doing a space-based remote sensing, when you want to look underground or underwater, you tend to use these very, very low frequency, long wavelength systems, and they require antenna systems that are huge. I mean, on the orders of tens to hundreds of meters long. And you can potentially, again, this is looking a little further out, you could potentially replace those receivers with a quantum receiver system that could fit on a small sat. So you don't have to have these long antenna arrays, or even these kind of antenna arrays that are flying in kind of a squadron formation. You can replace it with a single quantum system. And I think that's looking a little further out, but I think it's really interesting. We're in discussions with some transmit people that are interested in doing underground and underwater geo exploration from space, potentially providing the receiver technology for those applications.
And there's also things like power beaming, where the old space-based solar power would be wanting to send power down to a many mile wide receiving set of antennas on there, but there's still issues that get into it, like you choose a particular wavelength and that you still have a large size, but in theory there would be ways for you to massively compact that receiving array to and also perhaps even power beaming the other way to a low Earth orbit satellite, where the currently battery limited, where you could send power to it at high density, and then higher density means that you could up the transmit capabilities. So by giving it power, you up the transmit capabilities of the system, so that you can go to higher.
Yeah, I think, again, I think the sensitivity is a key point when you're talking about very, very long range communications or information transmission systems. If you're actually trying to distribute power, that's not an application we've looked at very closely, but the sensitivities, for initial insertion, a application that requires, again, very, very broad spectral width and high sensitivity is going to be a key one. Whether that's a comm system at very, very high frequencies, or whether it's a kind of an exotic exploration system at very, very low frequencies, kind of remains to be seen. But we're exploring both of them for sure.
Okay.
Yeah, and I want to be mindful of your time, Max, too. I know we're at 11:30. Wanted to just see, Brian, if you had any last questions, and I'll be sure to send the link to you of the recording.
Yeah, any write-ups, any presentations, any video in regards to the quantum RF, the 3.5 programs that you have, 6G applications, I'd be interested in that. Any graphics, so I can probably write them up separately, each one being a wide and deep thing in terms of the atomic clocks, quantum RF, and then the military repeater thing. I probably have to split the quantum clock one into the commercial and the military side, because it gets fairly in depth quickly. And then I probably have to split the quantum RF one, I guess, into certain other applications, because it's a laser. The lasers. One question about lasers. Are you doing some kind of like semiconductor emitters or something like that in order to compact them, or is there some other method that you're doing that?
So for the laser systems, we're mostly looking at semiconductor lasers. But what we're really interested in is using PIC, photonically integrated circuit technology, in order to integrate the active modulation elements, which are essentially a requirement for most of our technologies across essentially all of these areas. The modulation is key for clocks, especially. But almost all of these technologies require some element of modulation. Whether or not that's a 2-chip solution or a single chip solution remains to be seen. But there is a lot of pretty advanced work coming out of the PIC community that we'd like to target to our specific wavelengths in order to take advantage of essentially the cost down that's enabled by lithographically defining your lasers. That's the direction we're looking at.